Hello class, this tutorial will introduce you to not only use single gram and the single term as predictors, but also how to generate bigram, which is two terms together, and 3 gram, three terms together as predictors for the sentiment classification. And also we will introduce two methods for feature selections. First of all, let's load all the necessary library. Well, if you want to generate the engram like bigram and 3 grams, you need to load this library rweka. And also, if you want to do the feature selection, here we use the two methods that are from the fselector library. We will also still use the movie one dataset, the movie review dataset, and as we all know, we need to first convert our label, the label column, to a factor variable with two levels, positive and negative. And the next step is also mentioned in our last tutorial to change the review string encodings to UTF-8. And well, this time we also have 2,000 reviews, and 50% of them are negative, and another 50% are positive. The next step is also partitioning the dataset into training and testing datasets. We will do it by following our own routine, like randomly generating 50% of the rows to construct our training dataset, and the rest 50% will be further partitioned to testing 1, testing 2, like each of the testing samples will include 25% of the instances of the reviews from the dataset. And well, next we will show you how to generate bigram and 3 grams. Well, before we do that, we need to first pre-processing our reviews. So like we mentioned in our prior tutorial, we need to first convert our reviews into a corpus, and then change all the letters into lower cases, and then remove numbers, remove stop words, change the words into their stem formats, and also remove punctuation, and also remove those white spaces. Well, next we will introduce you using one approach of how to generate engrams in R. We will use this Engram Tokenizer function. Well, this function will split a string into an engram with minimum and maximum grams. So here in this parameter weka control, we kind of specify the minimum gram is 1 and maximum is 3. So using this function, we will combine all the single gram, bigram, and 3 grams from the corpus together. So let's generate all the single gram, bigram, and 3 grams from this step 6, this cleaned corpus, and save them. And then include all the grams as the columns and the reviews as rows. And here we use the term frequency as the cell values. So what are the single gram, bigram, and 3 gram? Here is one example. So for example, we have a sentence A, B, C, D, E, and all the single gram are A, B, C, D, and E. And for the bigram, we have A, B, B, C, C, D, and D, E. And for the 3 gram, we have A, B, C, B, C, D, and C, D, E. So these grams are generated in sequence. So let's see. So the dimension of this document term matrix with engrams, with single bi and trigrams, uh, is much larger than the single gram document matrix. Well, here we can see like we still got 1,000 rows, 1,000 reviews. However, now we have uh, a 600 more than 623 thousand terms. Next, we want to remove all these sparse terms, still using this function, remove sparse terms function. And we want to remove the percentage, sparsity percentage, or equals to or larger than 50%. And then we will like remove all the sparse terms and remain only 1,032 terms. Well, next we will create a vector only saved the frequent terms like from training data set into the string backup word 3G95 variable. And then this variable should include 1,032 different frequent terms. You can see instead of only single term, we now have several bigrams here as frequent terms, seem like, so on and so forth. Well, next, we will transform this document term matrix into a normal matrix in order to create our training data frame. And let's check the first two reviews and the term frequency of the first 20 terms. So instead of using binary weights, now we only use term frequencies as the values in this matrix. Well, similarly, we will calculate the top 20 terms with the highest term frequency. We'll still use the column means and sort them in descending order, and then calculate the average of this of the term frequency of these 20 terms. Well, now let me show you these 20 words in this bar plot. Well, you can see that all the terms with the top 20 words with highest frequency are all single gram. And well, we will construct our training data frame by attach the review label similarly. And then next we will generate our testing one data frame by first cleaning the reviews from testing one, these 6 steps. And next, we will also generate single gram, bigram, and trigrams for the corpus from testing data 1. But we only calculate the term frequency and only include those term frequency from the terms that from the training frequent terms. So here we add an additional parameter tokenize equals to Engram Tokenizer. But here is a dictionary. We will only want those 1,032 frequent terms from training dataset to construct this document term matrix. And here we also use the term frequency as a value inside this document term matrix. Um, well, as you can see, we still have like 1032 terms, and the review number is 500. And similarly, we transform the document term matrix to a normal matrix and then construct this testing one data frame by attaching the label to this matrix. Well, similarly, we also compute and demonstrate the top 20 words with highest term frequency from testing data 1. And you can see similarly only like single gram are inside this top 20 terms. Well, similarly, these are the basically same steps used to create the testing 2 data frame. We also only use those 1032 terms, including single gram, bigram, and trigrams, to and calculate the term frequencies from testing data 2. And here is the graph, the bar plot from testing data 2. Because we're using the term frequency as value instead of TF-IDF, so the words, the terms such as film, movie, want, like, make, get are have the highest term frequencies. Well, we will construct the sentiment classification models using this 1032 frequent terms, including single, bi, and trigrams. And the classifier we're going to use is still C-tree, decision tree, naive Bayes model from E1071, and also kernel support vector machine from Kerlab. Because now we have more features, more predictors, it may take a longer time to run. And here are the evaluation results for decision tree model using testing data 1 and then testing data 2. So the average overall accuracy can be 65%. And then we use naive Bayes model, the average overall frequency can be 68%. And for the kernel support vector machine, well, the overall accuracy can be 80%, can reach 80%. But it will take a long time to run, so we want to select the features that contribute most to the target variable. So we not only save the computation time, we probably reduce the probability of feature overfitting problem. And well, we will only introduce two approaches here. Well, these two approaches, the computation time for these two approaches is small, but ideally there are a lot of better feature selection algorithms and you could explore. Well, these two approaches are from F-selector packages from R. Well, first of all, we will use the chi-squared function. Well, this is the matrix with 1035 frequent terms as columns, and the first parameter is similar to the parameter we used to build the sentiment classifier. It is the y is a target variable, and we used 1032 two frequent terms here as predictors. So this chi-square function will basically test this chi-square statistic will basically test the independence of target variable and the predictors. So here is the chi-square statistic formulation. So here N is the number of documents and E is the expected frequency, and the T is a term, L is the class levels, and D is the document. And based on the chi-squares, so there is a weight calculated by this function and for each frequent terms and assigned to the terms, and we save them into chi-squared weights. So let's check the weights. So you can see a lot of weights are zero, but there are some non-zero weights. Well, next we will use this cutoff.k function to select only 175 terms based on these weights. Well, these terms will saved into this variable subset chi, and it is a collection, it's a vector of terms. Well, next, based on this 175 terms, the select features will regenerate the training dataset. Well, we will still attach the label to this matrix. However, instead of using all the 1032 columns, we will only use 175 column, those 175 selective features, and using data frame function to combine these two together. And now in total, this data frame has 176 columns. One is for target variable, and the rest 175 are for the predictors. Well, similarly, we want regenerating testing 1 and testing 2 after feature selection. Only use those selected 175 features based on the chi-square statistics. Well, next, we will gonna still use decision tree naive Bayes model and kernel supported vector machine to generate the sentiment classification models and then evaluate them using testing 1, testing 2. Well, because we now only have 175 predictors, well, the computation time is very small. So not very small, but much smaller than we used the original 1032 predictors. So let's see the prediction results. And well, this is the results for this is the decision tree results for testing data 1, and this is for testing data 2. So basically, the average overall accuracy is also around 65%. And for naive Bayes model, the average overall accuracy is more than 70% for both testing 1 and testing 2. While it performs better when we use those 1032 predictors to build the naive Bayes model. And for the kernel supported vector machine, well, the performance overall accuracy is close to 77%. So it is close to what we had back using the original features before the feature selection. So basically, by using the feature selection, we can solve the feature overloading problem, which may cause long processing time and also overfitting problem. Well, here we can run the program very fast but also it didn't hurt our performance. Well, next we will use information gain to calculate the feature weights. Well, information gain, we have learned information gain back when we start the decision tree algorithm. And similarly to chi-square, the first parameter is also the function, like y is the target variable, and the also using the rest predictors, 1032 predictors. And we save all the information gain weights of those more than 1032 terms into this IG weight variable. And we can take a look at those weights. And then we also can select a subset using the cutoff k function. We only select 175, similar to the previous procedure. And then we now have 175 selected features, and we only want to include these 175 features into our training data set. So similarly, we create a data frame with only these 175 selected features, and then we regenerate the testing 1 and also testing 2. Well, similarly, lastly, we use decision tree and Bayes model and also support vector machine model to test the to generate those model and evaluate the performances using training and using testing 1, testing 2. Let's see the performance for firstly. So first of all, let's see the performance of decision tree model. Well, this is for decision tree. So it's not the performance for this. Oh, this one is for decision tree. So the average accuracy, overall accuracy is also like about 64%, and the overall accuracy for naive Bayes model is about more than 70%, also performs better than the original naive Bayes model. And for the support vector machine, well, it is close to 76%. While the original support vector machine can reach the accuracy to about 80%, but it's close. The performance is close, but the computation time is much smaller. So those feature selection approaches, if you're interested, we can show you like other approaches, other like feature selection algorithms in R. Like you can try them offline, and they are like the effective ways to solve the feature overloading problems. So basically, this is all we have for this tutorial. See you next time. Bye.